Yeah. Maybe there will be some practices for the students after you finish the first session of the talk, or question and answer session.
There will be question and answer session later.
Okay. All right. Yes. Okay. Okay. We will be having this guest lecture maybe 1.5 hours yet. Okay, yeah. Including the question and answer session. Right. Without further ado, I will be passing the session to Dr. Nipras. Please welcome Dr. Nipras.
Okay, Bismillah ar-Rahman ar-Rahim. Assalamu alaikum and good morning. Thank you for inviting me to give this topic. Okay, today we are going to talk about memory management and operating system. Before we start, okay, let me share the screen. I cannot share.
I have allowed the share screen to them. You can retry that.
Okay. Yes.
Yes, I can see it clearly.
Okay. Okay. Today we'll talk about the memory management. But before we go to talk about memory management, okay, this lecture will cover some of introduction about the memory. Then we'll talk about the memory management requirements, memory partitions, bagging, segmentation, and bag replacements. Actually, I try to highlight the most important things regarding the memory management. Actually, memory management is huge, and a lot of responsibility and tasks should be done by the operating system. Okay, so before we go to the lecture, I want to ask if someone can answer from the students. What do you think about the memory, how the operating system can manage all this information and all this data, how can control this data? You have idea, anything can just pop up the class now? Anyone can answer?
Yeah. Any ideas, everyone? Yeah. Please raise your hand if you have any ideas about the.
Yeah, you can just raise your hand and open. Okay,
Yeah.
so maybe early
Yeah,
sleeping.
it's shy. Maybe check the.
It's okay, no problem. It's fine. It's fine.
Yeah.
No problem. We'll continue. I guess I want to warm up the session. Okay, so we know the computer system actually is a complete system, and including the software and hardware, all of these parts is working together. Okay, so the hardware, which is the components, we know these things, and software, which is operating system part of it. Okay, so we have the user who is the main importance, who can decide, especially for the multi-programming computers, multi-programming systems. Okay, so it's not a unit programming. So the unit programming system that can be controlled directly. So the memory will be divided, we can see, between the operating system and the program currently used. So when we talk about operating system for the memory, so that means there is allocation for the memory specific for operating system to be worked. Okay, we know the operating system, whatever we have, Windows, Linux, any OS that you are using, have specific files. This all files who manage all the devices, all the connected devices, all the parts inside the systems, the kernel. Okay, so there is interface between the applications and the hardware. Okay, so we have also part for the programs that executed during the running or during the system working. Okay, so for multi-programming system, the user is the main important things who have to control and manage this operations. Okay, because sometimes the operating system to do some things or to execute any trace or any operations, okay, maybe we'll wait for some input output devices. These input output devices will be restricted by the user. So user only when he have time, he can use and feedback to the system. So the user is the most important. Okay, so we cannot expect the time, how much time will take waiting for the input output to process or to be, if it is idle. Okay, so the operating system include 4 essential subsystem managers: memory managers, processor managers, device managers, files managers. Each of these subsystems work closely with other managers. Okay, but also every section have its own performance. Okay, or the unique rules that can perform and do, because different responsibility from different subsystems. Okay, so today we'll focus about the memory manager or the memory management. Okay, so memory management means everything regarding the memory, how can running move the data or the program or the process, okay, from the hard disk or from whatever we have to be executed by the processors. Okay, and also we have process managers, device manager, file manager, all these stuffs. Okay, I think most of you should be aware about it and know about it. Okay, so even if you see just only, for example, for Windows, okay, if you just right click on the Windows, I mean the computer, you can see the device manager, you can show all the devices that connected in your PC, and everything have the configuration, the setup. You can go to the drivers, software that you use, you can control and configure everything by using this device manager. But sure, there is part which is done by user, and there is a hidden process which cannot see by the user. Only the system can see. Okay, the system can see. You cannot see. Okay. Okay, so the memory management, we have logical addresses. This is some of terms or concepts we need to know. Okay, when we talk about the memory management. Okay, we have the logical addresses, which is generated by the CPU. Okay, this referred as a virtual addresses. Virtual addresses. This will be shown for the users, almost show for the users. Can contact physical addresses seen by the memory unit, by the system only. Okay, the frame, a fixed length block of main memory. You can see just here this figure is a symbol figure actually. Okay, just to show inside the physical memory. Okay, this is a frames. Okay, each page we have to fixed. Okay, is a fixed length block of data that receives secondary memory such as disk. A page of data may temporarily be copied into a frame of main memory. So how many pages we have should be allocated same number of frames inside the physical memory. So this is for the disk that we have, or the program that we have, or the file that we want to proceed. Okay, so after that we'll move to the physical memory. Physical memory, this one, the CPU deal with it, okay, and contact with it and proceed with this physical memory. Okay, later we can see how it's happen, how can move the pages from the logical or from this disk to the memory. Also, we have the segment. Segment is a variable length block of data that resides in the secondary memory. When we talk about secondary memory, we talk about the storage devices. Okay, we talk about the storage devices, which considered as secondary memory, because we know that the primary or the main memory, which is the RAM, and the main memory that can direct connected to the CPU. Okay, so the segment, when we talk about the segment, is temporarily copied into available region of main memory, which is segmentation. We call it segmentation. We talk about it later also in this lecture. The segment may be divided into pages, which can be individually copied into the main memory. Okay, this combined segmentation, and we call it bagging. So we can just now extract out, understand that is bagging coming from the segmentation. Then we come and we go to the frame or to the physical memory. Okay, so first we have a segment, then we have the pegs, then we have the frames inside the physical memory. Okay, so this is the main parts for the memory management. We have the memory management requirements. Okay, what we should do before do the war. Okay, we talk about the memory itself. Okay, then we have memory partitions. We have the pegging, segmentation, and peg replacements. Okay, so why we talk about this? Everyone we can. I mean, each part we talk about it separately now. Okay, so from the beginning, we have to relocate. We talk about the relocation. Okay, so we cannot run any program. Okay, if we don't have this program. Okay, cannot. So we have to know where we can put this program, or we can put inside the memory to be, I mean, during the execution time. During the execution time, a process may be often relocated in a main memory due to swapping and convocation. Swapping means enable the OS to have a larger pool of ready execute process. Convection enable the OS that have larger contiguous memory to place programming. Okay, this is what it means. Now we want to run any program. Okay, for example, Zoom. Now we are running Zoom. Okay, this software. Okay, we should allocate place to put all this software. Not, I mean, all the compact files. No, the running file, that the system files that need to be executed to make the program working well. Okay, so we know that this software or these applications have connect to different devices for the camera, sounds, screen, keyboards. All these devices have to be interact and connected, and also how to run all the commands that mean I mean to show all these graphics in front of us. Okay, so we know how much the size of our memory and how much is this program need to be used. Okay, we know some program when we try to run, they said, oh, this one will take more space in the memory when running. Okay, now when I run this software or this application, my PC or my laptop become very slow. Why is this become very slow? Okay, why this become very slow? How it's work? If it is only I have the memory, for example, 8 GB or 4 GB. Now we talk about the new devices. Before we have only few megabytes. Okay, so this will keep this system or these files, okay, temporary, and will divide it in segmentation, then will pass to the memory. Okay, these things to process in the system, okay, because they have sequential operations have to be run. Sequential operation have to be run. Okay, so how to move these operations or this process from the main memory that should be executed, okay, and to another one that still standby or waiting to be used. This is simple architecture for the program. Okay, you can see the program. This is the program and data. This is the stack inside inside the memory. And okay, and increasing the addresses variables. Okay, we can see here. Okay, and this is the process control information. Okay, so the data will start from the top of the stack. Okay, then going up. So the program and the data have to be connected, and we have all this information should be known for the memory to manage the process. Okay, so swapping, which is the important part in for relocation. Okay, so swap out process need to swap back into the same physical memory, depends on the address binding method. Okay, so why we need this swapping? For example, now, okay, when I run my Zoom, I said just now, okay, before that I have many applications maybe is already running during the startup. Okay, during the startup. Okay, many of us they run or execute startup applications for antivirus, maybe monitoring, maybe other communications applications that now most of us are using. Okay, so some of these applications may be not used. Okay, so it's just ideal or really not. It is active, yes, but not working on it. It is no interaction, no interact, no completely active. Okay, so and now I want to run new application or new process. Need to move this to the physical memory, to running to proceed. Okay, so we will take the existing one, which is already there but is not running. Okay, is not running, and move it to the other place. Okay, so and put instead of it the new process that I need to run. Okay, so which one I have to take out from the physical store or physical memory, or we call it here backing store. Okay, okay, and also the physical the memory itself. Okay, so there is some of algorithm or some of methods. Okay, based on that we can select, okay, which one we should delete or we should replace, okay, in the memory. Okay, we have the backing store. This fast disk large enough to accommodate copies of all memory images for all users, must provide direct access to this memory image. Okay, so later also we have to share. Okay, maybe some other user we want to use this kind of application or this kind of systems. For our computer or our PC, we can run multi-user. Okay, so we can see when we download any applications or any software, specific the system or that software that need system support. Okay, they ask you, you want this application only for this current user or for all users? Okay, why he asked you these questions? Because there is some of configuration, some of setting, the system itself will give this authorization or the permission, okay, to access to this specific files or specific process during the running, not only the files that store in the hard disk or in your place, I mean in the storage place. Okay, so based on this configuration, based on the authorization, okay, they can give the access. So there is some of restriction, okay, but in the same times, this file or this systems or these processes that need or expected to use from another users, okay, supposed to use from the same place in the memory. So no need to reallocate again and upload again to different place so connected with the other users. Okay, so we better to optimize the performance, okay, to use the same files. So we keep it for return back again. So rule out and rule in swapping variant used for priority-based scheduling algorithm. Lower or a priority process is swapped out, so higher priority process can be loaded and executed. Major part of swap time is transfer time. So only the transfer time, this is the consuming time during the swapping. Okay, so it's not just only actually the addresses. Okay, so the system maintains ready queue for ready to run process which have memory images on the disk. So later this image that in the disk can return later to the physical, okay, physical memory. Actually, based on the configuration or how desire to return back to the memory. So these figures can show the operating system, and this is the user space, and we have here the backing store. So how can swap? So the operating system can connect direct with this space, okay, with this space. Okay, so in next process, to put the CPU, okay, is it not in memory? You need to swap out the process and swap in the target process. Context switch time can then be very high. Okay, so if we have 100 megabyte process swapping to hard disk with transfer rate of transfer, okay, the time of the need for transfer from the secondary place to the memory. Okay, so we have this time to have to be considered during our process or during our programming. Okay, if we do this kind of programming. So how we can reduce the size of memory swap by knowing how much memory really being to used. Okay, so the important things, okay, we have to know the memory that need to use. Okay, for example, all of us are maybe most of us programmer, okay, we develop systems, we develop any applications. So when we are trying to declare or identify the data type or the variables or any data structure in our program or in our applications, okay, we have to know how much we need, okay, how many bytes. You just not just only take the maximum, because the default will take the maximum. Okay, so you have to allocate the specific place. Don't waste the memory space. Don't waste the memory space. Okay. Okay, so as I mentioned earlier, there is some of concentrates, okay, especially for the input output. When this input output devices, okay, is related to this process, relating to this process or the process that already running or executed in that time. Okay, so this one, any application or any process that waiting for input output, we shouldn't be move. Okay, maybe this will be make any I mean error or wrong during the execution. Okay, so here we can see known as double buffering address overhead. Okay, this what I mean in the input output. Always transfer input output to kernel space, then the input output devices. Okay, so before that we can we call it double buffering. We know now the new devices, okay, most of it have its own memory space, okay, or some of them have its own processors. Okay, some of the attached devices or adapters. Okay, this one will speed up the process, okay, and make the performance is more better. Okay, but standard swapping not used in modern operating system. Okay, this is a modified. Okay, so for reallocation, any question for that part before go further?
Yeah, any question from the class? You may ask some questions to Dr. Nipras along the way of this webinar session. Yeah.
Yeah. During
Yeah.
each section, each can ask, no
Yeah.
problem.
There's 100 plus students, Doctor, joining
Oh,
this
I see. So I need to.
103 students. So
Okay,
everyone
okay.
is very
So
interested to join this.
continue.
So
Okay, no, no,
yeah.
no, no,
Okay.
no, no problem.
Okay.
Okay,
Yeah.
then
Yeah.
later, you can send me email or anything else with the subject of the seminar topic. Okay, so the second requirements, protection. Okay, so before because we to do the management, okay, the memory management, we said we have to allocate space for the whatever we want to process. Okay, whatever we want to put in the memory, we have to allocate space for this. This is why we call it relocation. Okay, second things, the protection. Process should not be able to reference memory location in another process without permission. This is what I mentioned earlier, okay, about the access to the data. Impossible to check addresses in program at compile load time since the program could be relocated. Address references must be checked at execution time by the hardware. So each process should be protected against unwanted interferences process. Okay, even the process itself or the system itself, we have to make it protect. Okay, whether accidentally or intentionally is happen. Okay, so the program should not be able to reference memory location in a process. Okay, without permission. So we have to, I mean, the system itself concern about this one as one of the restriction, okay, to protect the memory and to protect the system. Okay, so I'm sure maybe this one happen for any one of you. Okay, if you try to run something or during the programming, if he want to call some commands or something, he will get error message from the system. Okay, cannot access to this part of the memory. Okay, so user process cannot access any partition, okay, of the operation, either program or data. Okay, so have to give the instruction, okay, to give this permission. Okay, without this permission, we cannot access to any part of the memory or even the system itself. Okay, even the system, not only the memory. Okay, we know in sometime in when you even in the hard disk itself, if you have some of files and you have multi-users, okay, some if you log in another user, okay, we cannot see the files that belong to other user unless he or she, okay, make a setting or configuration to allow to other users to access to his parts. Okay, this will lead us to the second part, which is sharing. Okay, so relocation, protection, sharing. Okay, so in sharing, any protection mechanism must have flexibility, to allow any user or the several process to be accessed in the same duration. When we talk about same duration, same space in the memory, we talk about the memory. Okay, if if number of processes are run executing in the same program, okay, is better and give advantage to allow to each process to access to the same copy of the program rather than have its own spread copy. So this one, when I give you the example about any these applications, we not talk about applications only. Okay, we talk about another software, another drivers. Okay, maybe now I'm using the monitors. Okay, I'm using the monitors. In the same time, I will run another application that use the monitor to present or to show the information. Okay, to show the information. So should be give access inside the system itself. Okay, so can go to the, when we talk about the file that connected and the interface between the system and the hardware. So this one also is uploaded actually in the memory, uploaded in the memory. So no need to, maybe if we cannot access and use this specific files or specific devices during it's already in use, okay, so sure the program will not be run, okay, cannot be run. Even now, we are using the Zoom and we use the mic, everything. And if I want to open another applications, even during my talk, okay, and these applications need to use the camera or need to use the mic, okay, even if I'm not going to open the camera or open the mic, okay, he will give me a message. He told me the camera is in use, okay, maybe will interrupt the application and the application will not running, okay, for same things for the mic, okay. Also in the opposite side, if my mic, I'm sure this happened for some of you, definitely, okay, if your mic got problem or connected with other devices and you try to run the Zoom, okay, we can see the Zoom will running, okay, but the mic will be show you a signal or the sign on top the mic, so there is a problem or cannot connect to that device, okay. Actually the device, when you check, the device is there, okay, and the driver is there and is working probably and everything, but cannot connect. Why cannot connect? Because it is in use, okay, or still in the background, okay, connected with another application or another software, okay, in the same time, okay. So sharing is also one of the requirement for the memory management. Okay, so here you can see some of main points. So must allow several processes to access commemoration of main memory without compromising protection. Better to allow each process to access the same copy of the program rather than have their own separate copy. Cooperating process may need to share access to the same data structure. Okay, this reflects the same things what we mentioned. Okay. We have logical organization, also physical organization. Okay, so the logical, when the user write their program or their models, okay, have some of characteristics. Instruction model, okay, for if it is this one is will be for execute only, it will be for reading or writing or read only or write only, okay. So this instruction have to be given, okay, in the logical organization, okay. Also either private or sharing with public. This we can see the connection between each part, okay. We now connecting with the sharing, connecting with the protection as well, still in the same things, but from different perspective view, So to effectively deal with user programs, the OS hardware should support basic from the model to provide required protection and sharing. So this will happen where in the logical organization. Mean the user will do this configuration, he will or she will do all this what you call it, setting, okay, to instruct the system, okay, how can deal with this information or this program, okay. This we call it the logical organization, okay. Organization mean how to organize the things, okay, not organization the institution or other things, okay. Again, for the physical organization, Okay, external memory is the long-term store for programs and data, while main memory holds program and data currently in use. So we have two memory, okay. The external memory, which the store for long term, and the main memory that will connect with the CPU or with the processor in the same time. Okay, the information will move between these two parts during the execution or during the process. Okay, so the memory management will control this movement. Okay, will control this movement, which should be more efficient. Okay, and will take all the responsibility. Okay. We can see here in this figure, okay, for about the memory partition. Can see here this one is divided by fixed size, and this one divided by not equal size. Okay, this is equal size and not equal size. Okay, so we talk about relocation. Okay, so that's mean we have to relocate place, but we didn't talk about how much we can give to this program or this specific process from the memory. Okay, because when allocate the space, okay, that's mean this space cannot access and cannot be executed or any unauthorized party. Okay, so in most scheme memory management, we can assume that the OS occupied some fixed partition in the memory. Okay, as I mentioned earlier, for the memory is have to divide it first. Okay, there is a one partition will be fixed for the operating system or the system itself. Okay, the others can be used by the other applications, and also this part have to be partitioning. Okay, so why have to partitioning? To give more or more applications or more programs can be used in the same times. This the more good things, okay, in the new computers and the modern computers, that we have multi-processors. Okay, we have multi-programming. Everything can be run in the same times. Okay, so how we can do this? Okay, we can see here, this is fixed size. Okay, that's mean when we have a process should be in the same size of this partition, okay, otherwise cannot be fit, so we cannot fill to this specific memory unless the space or the location will be the same size. Okay, so but actually for someone, actually I won't ask, but I don't know, again, the number of the students will start me. Okay, there is advantage and disadvantage. Which one is better? We have to use the fixed partition or fixed size partition or an equal size partition. Which one do you think is better? Okay, so based on the system, based on the applications, or based on the use of the computer. Okay, so the number of partitions specified at the system generation time of active, not suspense process in the system, because the partition size are present at same generation time. So this one cannot, you know, play around or cannot fix. So from the beginning, when we set up the system, or when we build the system, we have to fix this one. So user cannot do this. Okay, but the process, I mean, for the example, the company that product this kind of system, okay, we can do this setup, okay. Also from the kernel, from the setting, I mean the BIOS things, okay, not the high, I mean the high user interface or high user configuration, okay, because we know the setup for the kernel devices cannot be done unless to go to the low level of the system, okay. This is the things. Okay, so now we'll move to the next slide for more clear, okay. With this example, we can see this example. The partitions are created dynamically so that process is loaded into a partition of exactly the same size as that process. No internal fragmentation, more efficient use of main memory. Okay, compared to this one, okay, compare the fixed one. For example, now I have process, but this process we can see here each part have 8 megabyte. Okay, 8 megabyte. Each partition have 8 megabyte. If my process only 5 megabytes, okay, so we'll use this 8 megabytes, okay, will be allocated for this specific process or this specific program, but we will waste 3 megabytes if only because this partition, okay, will be in use, okay, will be in use. So this one of the disadvantages as well from the fixed equal size, okay. So we can see this example, okay. We can see this the first one, A. Now the operating system is have all this 56 megabytes, which we call it whole. Okay, so now the process one will take 20 megabytes, okay, which allocated based on the size of the process. Okay, this one allocated based on the size of the process. The second process will take the second place. Then the third process will take the third place. Okay, now here what happened in this part? In this part, what happened? We can see the remain space here only 4 mega. Okay, 4 mega, but there is one process coming, okay, which more than 4 megabytes. In this case, we have to make swapping. We have to make swapping. So which one will be swapped? Okay, this will swap. For example, let's just assume, okay, the process 2. Process 2 will take out in this part, okay. Then we can see the process 4 coming. Okay, so maybe the process 2 swap or finish. Okay, swapped or finished. So we can see process 4 here, okay, only 8 megabytes. So still we have here the 4, and also we have here 6. We have the 6. Then process 1 also here will be put out. Okay, so another process come. So now we can know the process 2 where process 2 come again, okay, after finish the process 4. So maybe this was ideal. Okay, as I told you, based on the method that we are using, okay, but this one to show how the partitions can be benefits, okay, for the memory management and efficient use of the size of the memory. Okay, so dynamic partition is more better than the fixed partitions. Okay, but maybe there is some of problems still there for the fixed and dynamic partition scheme. Okay, maybe there is some of drawback. Definitely there is a drawback, because fixed partition will limit the number of active process. Okay, so the space also maybe will use in efficient way. Okay, so if there is some of available partition size that can be merged together to run a big or another process, will be cannot be done because that part already allocated for that specific program or specific process. Okay, also the dynamic partition scheme more complex. Okay, more complex, and also overhead on the convocation, because have to take out the partitions, I mean the process from the memory to swap to the second memory, okay, secondary memory, then return back again to the process. Okay, so they come with this another method for partition. Okay, we call it body system. Okay, in this body system, memory blocks are available of size 2 power k words. Okay, k between L and U, between L and U. Okay, we can see the upper and the lower, the maximum part and the lower part. Okay, for the size, I mean the allocated size for the system or the program. So 2 power L, smallest size block that is allocated. Okay, largest size is 2 power U block that allocated. Generally 2 power U is the maximum size inside the memory available for allocation. That's mean if I want to allocate all the whole memory which is available, we can use. Okay, this is what we call it. So both I mean any user, I mean any application can be run and can be allocated based on the size. Okay, so we can see here in this example, okay, this is a recursion algorithm used to hold the size. Okay, this is the algorithm, how is body system is work. Okay, we can see here. Okay, we'll check the size, okay, of the process. If the size of the process equal U plus 1 or greater than U plus 1, that means will be failure, because you are required space more than the space available or allocated for processing. Okay, but if the I list empty, we can get a whole and split whole into bodies. Okay, so from the beginning, we'll split the whole in bodies. Okay, means different part, because we talk about partition as well. Okay, why we have to split in bodies? Okay, to reach the specific size or the right size that we need to use. Okay, that we need to use. We can see here in this example. Okay, so from the beginning we have 1 megabytes block. Okay, the request is 100 kilobytes. 100 kilobytes. So from the beginning, okay, we'll divide into 2 bodies. Okay, 2 bodies. 512 kilobytes. Sorry, then other 512 kilobytes. This 500 kilobytes will divide it in 265 and 265. Then the 265 will be divided in 2, which is 128, 128. So 128 is the closest to the 100 kilobytes, which is requested to process. Okay, now we receive another request. we receive another request which required 240K. 240K. So now this one is allocated for A. Okay, and we have here 128K, but here we have 256. So this one match with the required or with the requested space to allocate. Okay, so B will be allocated in this partition. Allocated this partition. So again, request 64. So we have 1 to 8, which can be divided, okay, can be smallest to fixed 64. So here we have 64, 64. So now the available memory, we have here 64 and we have 512K. So now again, we have 256. Okay, 256 requested, okay, in this part. So where we can put this one, okay, here only in this part, the available only 64. So we'll go to the second part for the beginning. If we consider these two parts, okay, we'll divide it into bodies. So this body will be 256 and 256. So D, I mean this request, the new request will take this partition. Okay. Now, again, we release B. Release the process B, which is how much B? 240. Okay, 240. Where is the 240 location? B. Okay, this one B. Okay, so this part, okay, this part will be released. Then we'll release A. So this is release A. So now this one will be free, this one free. So again, we have requested 75K. Okay, so 75K. Only we can take 128. Okay, because we are dealing for power 2. Okay, because the base is 2. We know the 0, 1, the main things for the memory space. Okay, so 1 to 8 will again take this block, then release C, release E, release D. So we come back again to all the available memory. So the important things when you are programming and you are allocating for you dealing with direct memory, okay, you have to release and delete your allocation after you finish. Okay, I don't know if you are in which level in your degree now. Okay, but for programming, when you use, for example, I give you a simple example of data type, the pointers. When we are dealing with the pointers for the linked list, okay, or the pointers, we have to allocate and create new pointers. This pointer actually direct connect with the addresses. Okay, direct connect with the addresses. So after you finish, you have to delete this nodes or these pointers, okay, and make it free. Okay, so this will save the memory, because if you didn't do that, will keep in the memory and the memory will keep aware about it. Okay, unless there is a specific method, okay, for replacing memory. Okay, so again, I don't know the. Okay, so this is can show in 3 graph. Okay, represent the body system, how it's work. Okay, we can see here the 100 first have to be 2 parts. So this is 2 parts again, 2 parts again, 2 parts again. Okay, so we can see here this just to show the leaf node that is allocated. Okay, and the leaf node for unallocated, and branches coming on. Okay, so again, now after we do the partitions, okay, one more thing is important. Now we talk about how the partitions can be done, fixed, dynamically, or body system. Now we again back to the relocation. Okay, relocation, we have relative addresses is the most frequent type of logical addresses used in the program. Okay, and relocatable models are loaded in the main memory with all memory references, okay, left in the relative form. Okay, so this will be connected with the logical addresses. Okay, the physical addresses are calculated on the fly as the instructions are executed. So we can see now later, I mean in the coming slides, okay, how we can calculate and make calculate the physical address that need, because we know the physical addresses, the memory only know the memory, the system, not the users. Okay, for adequate performance, the translation from the relative to physical addresses must be done by the hardware. So from these statements, when we call translate from the relative to physical, so relative means the addresses that located in the logical organization or logical place. Okay, we talk about the logical addresses. Okay, so hardware device must I mean, the hardware device will be mapped between the logical virtual addresses to the physical addresses. Okay, we talk about the memory. So we have the memory management unit scheme. This is the shortcut of the memory management unit scheme. Okay, so we'll do the allocation. We can see here in this figures. Okay. Okay, so this is the CPU, and we have the memory unit here. Okay, so the CPU sends the virtual addresses to the MMU. Okay, so the MMU sends the physical addresses to the memory. Okay, so we'll calculate and send the physical addresses to the memory. Okay, because the memory will manage all this, the memory management unit will manage the information that can go to the memory or take from the memory. Again, the addresses, how we can calculate, we can see here, the logical address 346, just for example, okay, then relocation register, okay, 40,000, okay. This number, okay, the base that's starting in the physical memory, okay, the base address, this is the address, okay, the base address, okay, that can start, okay, in the beginning, I show you there is the raw stack, after the stack only come the base, then the others application or process can be located in the memory. So the baseline or the base addresses is 40,000 here. So plus the logical address. So we'll go direct to this physical address. We'll go to the physical address. So we know the relocation space already from the previous slides, which is available on allocated, available to allocated for user or for any process. Okay, so we can here see the logical address have to be checked if it is lower than the limit registers or more than the limit registers. If it is more than the limit register, will be error, so cannot support, okay, to allocate this amount or this size. Then if it is okay, yes, we'll relocate registers for this process, for this process. Okay, so here we can see this figure as well. This is stack, and here from the stack, the base, okay, the bounded of the registers. Okay, we have the comparator here, interrupt the operating system if there is a problem. So the base register and relative address, this is from the logical. Okay, the logical will add the base address that we have in the example 40,000, will add together and absolute the address here. Here we'll compare if it is match with the available size or not, can be addresses or cannot. Okay, so after that can give the addresses. Okay, so now we know that the sequence, so about how the management or the memory management should be done, the requirement, okay, and also the partitions, how it's doing. Okay, now how we can put the data itself inside the memory, because from the beginning we talk about the frames, we talk about the pegging, we said about the partition, we said about the segmentation. So now we can see the pegging, how it's look like. Okay, so for the pegging, we can see here, this is the memory we said in the beginning. So each peg will be fixed to one frame. Each peg will be go to the one frame. Okay, so now we have 15 available frame here. Okay, so now we have the process A. Process A consists of 4 pegs. So the 4 pegs will come to the top. Okay, then again we have another process, we call it B. Okay, so we can see B here. Okay, again we can see here load process C, also 0 1 2 3 0 1 2 0 1 2 3. We can see the different. Okay, now we have left 1 2 3 4. Okay, 4 frames is available. Okay, now the swap out B here. Okay, the B will taken out. Why? Because there is another process D coming. Okay, see now the D, how many pegs? Okay, 0 1 2 3 4, which is 5 pegs. Okay, but you can see the place that the frame, the pegs take in the frames. Okay, so the swapped space, which has the 3 frames here, okay, will allocate for first 3 pegs, 1 0 and 1 and 2, and the rest of the pegs will come to the at the end of the frames here. Okay, so you can see here 0 1 2, then 3 4 here. Okay, so this how can the assignment the process to the free frames. So after this one, now we can see the pegging table, how it's look like, because I told you this addresses, the user don't know about it, only the system. So if the process of the users and the user part, okay, define the segmentation on 2 pegs, so we should know which peg refer to which frame, especially if it is not in the sequence way. So we have here this the pegging table, okay, or the peg table for each process. Each process, okay, will contain all frame, all pegs, where is located, in which frame number, in which frame address. Okay, so the process A, 0 1 2 3, this is the first one. Process B is empty because swapped. It is not in the memory right now. Okay, so process C nine, 10. We can see here process C. Okay, where is it? Yeah, this is process C. Okay, 7, 8, 9, 10. Okay, then process D also again 4, 5, 6, which are allocate for the swap space. After we swap the process B, okay, we use these three for process D, then the rest will be here. So it is no problem wherever you put the data. I mean, in the memory, still can access. Okay, so this how same like the directory files. Okay, same the directory files FTP the file. Okay. Okay. Okay, we come to the segmentation. Segmentation, which is to the user side. Okay, which is part of the memory management. So if we have any program, okay, because I try to match between this and your programming. So because you affect in the memory used by the programming and by developing the applications in the same times. Okay, so user program can be simplified using segmentation. So means the program, okay, can divide into number of segments. Okay, so we know that the program have different parts. Okay, procedures, main program, functions, method, okay, the variables. Okay, so all of the program be of the same length. Okay, although there is a maximum segment length, as with begging the logical addresses using segmentation consists of two parts. In this case, a segment number and an offset. Okay, because we need to know, okay, as I mentioned earlier regarding the partitions, okay, we have restriction the maximum limit. Okay, so at the same time the segmentation should be, okay, match with this limitation or with this restriction in the system. Okay, so whatever number of segment we have, we can will divide it, the system or the program, okay, should be not more than the length that already allocated or can be used. So the compiler will generate the segments, loader assign the segment number. Okay, the loader assign the segment number. Okay. Okay, this part done in the compiler side. Okay, when you are doing the programming, okay, you will do the compilation. Okay, the compiler, what exactly done during this time? Okay, we write a code. Okay, we write a code. Before we write a code in the beginning, we will put any libraries, any additional files that may use. Okay, then how can these libraries and these files, okay, will be run while I only write my code? Okay, during the compilation, first, after translate, before translate the code to the machine language, okay, also the intermediate code, okay, now we'll have to link to all these files or all these libraries. Okay, after link to do all these libraries, we'll load all this information or process in the same file, will be in the same file. All this will come back together. So the libraries, the other files that we will include functions, procedures from others. If I keep different procedures in different files separately, then I call these files or these functions, okay, but we have to include it in the top of the program. So all together will become one, like one file or one but actually this one will be divided and segmented by the system, okay, during the compilation, during the compiler generation. So after that, we generate the object files, Also, the object files, okay, will consider as segments as well. Okay, we'll consider as segments as well, because all this will run together. Okay, so many things happen during the compilation. Not only we just we write the code and we just make run. No, before run, there is all this stuff will be done. Okay, and based on this files or this connected information will be segmented. Okay, and upload to the memory. Okay, so can see here the user view of the program. We have the subroutine, stack, symbol table, main program, square. Okay, as I mentioned, user will specify, okay, address by two quantities, segment name or segment offset. Okay, this is the segment name. Okay, the main, stack, symbol, symbol. Logical addresses contain the tuple, segments, and offset. Okay, the variable size segment without order, length, purpose of the program, elements are identified by offset. Okay, this why I told you in the beginning, when you are programming, okay, or coding, okay, you have to identify well, you have to allocate memory well, okay, before use. Okay, you can see here this same the logical view segmentation. Okay, because here is the user view by using the names of the users, okay, that used. So here we can see from the logical view, okay, this is the segments number 1, 2, 3, 4, okay, which come from the user space. So this is the physical memory space. So 1, 2, 3, 4. Okay, based on the partitions and allocation for processing. Okay, so the variable size partition is very important. Okay, the variable size is play more important things in the when you're doing the coding as well. Okay, so now we'll talk about the replacement. Okay, we said in the beginning there is swapping. Okay, the swapping between the pages and inside the frames. Okay, and we said which one should be moved, which one should be kept. Okay, so we have to find first the location desired page on the disk. Find a free frame. If there is a free frame, then we'll use it. If no frame, then we'll go to the big replacement algorithm. Okay, to select, we said hit the victim frame. Okay, the victim frame, because will be the eliminate or replace from the memory. Okay, so bring the desirable page into the newly free frame, update the page and frame table. Continue the process by restarting the instruction that caused the trap. Potentially to page transfer for page fault, increase effective memory access time. Okay, so here we didn't talk anything about the algorithm yet. Okay, still we didn't talk about the replacement algorithm yet, because there is different algorithm. We'll talk about it now. Okay, guys, now we show the replacement how done. Okay, this is the frame, the valid frame. Okay, we have the back table, which is supposed to be updated. Start back in. So the new bag will be come in, the new bag, then the victim will be out. Okay, this is the bag store, okay, or the secondary store, okay, that keep the information. So this why if you go to your hard disk now and check the partitions, okay, you can find, I mean, if your hard disk, for example, 500 GB, okay, you cannot use the full 500. You cannot use the full 500. Even the system, the operating system will be, for example, allocated for 10 GB or 20 GB, for example, whatever, okay? So then still there is a partition cannot be used, which we allocated for the system. So this allocated for the system, okay, will be used for this process. We use to this process to support the memory, Okay, so we can see here, this is replaced here. Okay, 1, 2, 5. So now the number is updated in the table. Okay, in the table. Okay, based on what we replace these bigs, or based on what we choose this specific bigs to replace, okay, or to swap, we have different algorithms. So this one we have to choose during the setup. Okay, first in, first out. We know the concept is well known. I think everyone know. Okay, that's mean the first in, first out. That's mean which is coming first. So this one will be considered to removed. Okay, so this will be associated with the time. So we need the timer. Okay, and also to know which one is coming first. Okay, so if we can see these numbers, so the limitation of variable is initialized early to constantly used. Okay, so this one of the limitation. So we have to label all these frames. We have to label it. Okay, make a variable to know which one coming first, which one coming next. Okay, and also the timing. So all these things we need to take in account to run to work with this algorithm. Okay, so this is just to show. We have here the frames. Okay, this is the reference string, and we have 15 bigs fault. Okay, how to track the bigs? Just first in, first out. We can see the first in. This is the string number, so this is the number. Okay, we can see how we can replace the bigs. Okay, so this one, is it optimized or not? Okay, still we cannot deal. Maybe this one, which is the first in, okay, maybe still in use. Okay, maybe still we need this process to work with. Okay, so it's not optimal algorithm to use. Okay, so replace bag that will not be used for longest period of time. How do you know this? Cannot read the future. Use the measure how well your algorithm performs. Okay, so as I told you, we have parameters, variables to be used for count the frames and also the bigs. Which one is coming first? We can see here 7 and 70, 701, 201, 203. Okay, so this is the result from the previous operation. Okay, so it is not optimal to use the first in, first out. Okay, we have another algorithm, we call it least recently used. Okay, actually this algorithm, okay, actually we can use it not only here, okay, it applied here, okay, but you can use it in different place. Okay, this specific used for caching, we call it for cache memory. Okay, if you search about the cache memory algorithm for replacement, we will definitely find all this algorithm. So least recently used algorithm, okay, that's mean we'll check. This also need for timing, need for timer and clock to see which one recently used. For example, if you go to your files in any application for Microsoft Word or whatever, even the history of your browser, you see the recent pics, okay, you visit in your browser. Okay, so this is the same concept. So least recently used will be removed. Okay, so use past knowledge rather than future. So because the first in, first out, okay, we don't know about the future when this one will be finished to consider it, to take it out. Okay, so how long time I will wait until the existing process finish and go out, because cannot swap, I cannot directly if it is in use. Okay, and we cannot use another one unless we remove and replace with the first n. So they think to use the existing information, existing knowledge, okay, rather than the future. So now we think about the time, how recently used this process, okay. Then the list used will be taken out, or replaced with the new one. Okay, this is, we can see here the counter. Here there is a clock and CPU. Okay, so in the same time when do the addressing, okay, so every page will be addressed, will be calculate with record with the time of use. Okay, the time of use, we can see the latest time of use. Okay, so later when we want to replace, okay, when we want to replace, then we'll look in this column. Okay, we look in this column to see which one is the list recently used. So we have to implement stack, okay, to keep stack big numbers in double links listed for big reference, move it to the up, big time big in the down. So this is the bag. Okay, so we can see here A and B. Okay, first A, which is 2 here. Okay, this is the recent. Now after that we access we use B, so B become the top. So 1 1 0 4, because this is the seven, become to the top. Okay, because this is the recent use. So the list recent use, okay, will be 4. Okay, the list recent use will be 4. Okay. So again, less recent use needs special hardware and still slow, because we have to, calculate these all things. Okay, each big associate a bit initially 0. When big is referenced, bit set to 1. So extra and additional references need to be used. Okay, and we have to recall all these references, okay, for regular interval. And we have to keep 8-bit string for each pigs in the memory, because this will consider the number and the time. Okay, so regular interval time copies and reference, this one also will consume in the process. Shift the order base right side by 1 byte or 1 bit, sorry. Okay, so we can see here this approximate algorithm. Okay, we can see the period and here the time, and this is the bigs. Okay, so how it will be the clock tick and the big is okay. So be used. Okay, we'll keep chain. Okay, this will be add additional variable, additional computation in the memory. Okay, another algorithm can be used. Still, this is the less recently used, the same things that we just talk now. Okay, discuss for more explanation. Okay, to show how is the cycle and how it's work. Okay, so because the time going on, so I will continue to the next one. Okay, here some other algorithm. Okay, but because I see the time ready. Okay, okay, so now there is another algorithm we saw less frequently used. Okay, and most frequently used. Okay, so here we talk about less recently used. Okay, less recently used. Okay, less recently used. But here we have less frequently used. Less frequently used means is a different from less recently used. Less recently used, okay, maybe it's maybe not used too much, okay, okay, and the oldest one in the history, okay, we'll remove this, what we call it recently used, but less frequently used. For example, if we said in 1 week, for example, I use this application 1 time, okay, the second application I use 3 times, other application 5 times. So the less frequently used, that one I use only 1 time. This we call it less frequently used. So that's mean if I replace this biggest, okay, is not expected to be called or to be run in soonest, okay, so or in the near future, okay. So we prefer to delete the less frequent use. Okay, so based on the argument also, the big with the smallest count was probably just brought in and has yet to be used. So max frequently used, okay, this one should be not don't remove because maybe we'll use again. So all this algorithm, okay, will consider and use for the big replacing, okay, and cache replacement also as well. Okay, okay. So I think until here I should stop, finish, so I can give you time for questions and answer if you have any question.
Yeah, thank you, Dr. Nipras, for the very nice insight of the memory management
Thank you.
topic. Now I'm passing to the students if there's anything to be double check with Dr. Nipras
Yeah.
regarding the up to the memory management. Sorry, page memory replacement management. Yeah, this one is yeah, memory replacement management forms. Yeah.
Yes.
Algorithm, yeah, algorithm to replace data from memory in and out to make sure that memory usage is very efficient. Yeah, this is actually, if I can summarize, because the memory spaces are very limited compared to the processes and data to be stored in the memory. So we need to find ways to make sure that memories are efficiently used by designing algorithms and also from hardware perspective as well, that enables the efficiency storage for data in the very limited size of memory.
Right.
Yeah, now any question from the students related to this topic, please feel free to raise your hands, and I'm going to pass this opportunity for you to ask any questions to Dr. Libras. Anyone in the forum?
Yeah.
Yeah, let me check from my class. I'm gonna one of them.
Yes, okay, no problem.
Okay. Muhammad Rafif, are you here? Muhammad Rafif is not. Rafif. Rafif is not here.
Okay,
And
actually,
yep.
yeah,
And any
actually,
ideas?
the operating system, there is a lot of things. If we talk about the memory management, we talk today about the memory management from the operating system perspective. Also for the, if you are programming, also you have to aware there is some of, actually, because the time is not that this is why I told you we have to specific the topic about the things. Okay, so for programming, for example, how to manage the memory by using any language, for example, C++
Plus, yeah.
or Java. Yeah, for C++, the most, I mean, the most programming language that used for this topic. Okay, so the good example for you to practice about the memory, okay, the pointers, because the pointers work with the addresses. The pointers work with addresses. Try to, when you just make a simple code, okay, and declare the pointers, and try to print out, okay, the address, and print out the contents of the pointers. You will see the different. You will see the different, which is the different. And also you can print the contents before you assign any value. Okay, this you have to be investigate and to check. So this will be more emphasis in your mind about the memory, how it's look like, and how is the information that can be. Sometimes if you didn't assign a value, they will give you a random number, is it?
Yeah.
If you didn't make initial values for your variables, sometimes will give you the random numbers. Why? From where these random numbers? Because when you allocate, okay, this will be give you the maximum size, then randomly give the value inside the system, inside the allocation space, okay, to fix the size. Then you see this different value coming in. I think this simple example to you for practice the addresses for the memory. Yeah, Dr. Ari. Yeah, you can continue.
Okay. Well, thank you. I'm gonna call Anayu. Are you here, Anayu Sapita? Do you have any questions, or you can give your opinion about this topic? Anayu, are you here, Anayu? Anayu Sapita.
Iya, Pak.
Okay, you can submit your questions or maybe your inquiries in Bahasa Indonesia if you like, because Dr. Libras, I think, can also speak Malaysian, and that has some intersections with Bahasa Indonesia. Please
Yes.
go ahead, Anil. Yeah. Ya, ada yang mau disampaikan, Anil? Pertanyaan atau apa ya? Ya tidak hanya pertanyaan sih, misalkan menyampaikan pendapat itu juga boleh ya. You can also submit your opinions about this course. Silakan Aniung. Ya, Aniung. Halo, bisa dengar suara saya?
Iya, Pak.
Monggo, bisa disampaikan.
Sekarang belum ada, Pak.
Bagaimana kesannya terhadap materinya?
Menarik sih Pak, belajar banyak.
Apa yang tadi yang diingat coba? What things do you remember from the topic, from the top?
Sorry.
I'm asking to Aniu.
Okay.
Can you recall anything from what Dr. Libras have mentioned, have explained? Yeah. Okay. Right now, random fine. Shukra Wahyu Ramadan, are you here? It's not here. And then Ersya. Ersya? Muhammad Ersya Finorian. Can you hear me, Ersa? Ersa, are you here, Ersa? If you can hear me, please reply. Answer. Who else? Apinaya. Apinaya. Are you here, Apinaya? Apinaya, yes, he is here. Can you hear me, Apinaya? Apinaya, you here? Can you hear me? That's fine. If there's no,
Okay.
that's okay. Okay,
Yeah.
well, just we can just.
Our
Yep.
time is.
Yeah, it's going to getting closer to the Friday prayer. Yeah. Okay, Doctor, thank you for your time to give a talk. I hope I can see you in USM. Dr. Sahira just invited me to come to USM for the ceremonial signature for the internship and the short program between informatics, ITS, and USM. So to nice you in person later on.
Nice
Yep.
to meet you
Yeah.
here, inshallah.
Yeah. Can you give some kind of wrap up, like closing statements for this very nice webinar before we wrap up this session?
Okay, just the main things for this course, you have to be more understanding about the operating system, which is, is for us as computer science specialist, we have to aware about this all things, which is not hard actually to understand. Also, is same like our life. If you interact, the easy things, if you want to understand and earn more knowledge, just try to connect between any knowledge with the nature. Okay, any knowledge you want to learn, try to connect with the nature. Is look like what? Okay, so this the things, and I like to thank you, Doctor, for your invitation. Thanks for the students to be here, and I'm very happy to give you this fast and simple lecture today, and hope to see you soon, inshallah. Thank you.
All right, thank you, Doctor, for your time to give talk in this moment.
We can make group photo.
Yeah, sure. We can make a group photos. Sure. Hang on. Just remove the pin first, and then let's make a group photo.
Using the attendance or what is?
Group photo. How can we do that? Oh, you need to stop share your screen first, Doctor, and then we can
Yeah.
the group photo. Yeah.
Yeah,
Okay. Yeah. Can you all open up your cameras so we can do a group photo? Okay, because this is 2 slides, so I'm gonna start taking pictures from the first slide. Please be ready. Okay, 1, 2, 3. And then let's do the second slide is to be taken in 1, 2, and 3. Okay, thank you for your cooperation.
Okay.
Thank you, Director. I'll pass this I'll pass on the pictures to you via your contact. Right.
Okay.
See you later, everyone. And Dr. Dipras, thank you. And
Yeah.
see you next time. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
I'm gonna end the session. There's a quiz in the chat room that you need to do, guys. So just a feedback for my team and also for this operating system course. Right. I'm gonna end the session in 1, 2, and 3. See ya.